Let's go ahead and solve another question from the major loss concept. And in this one, it's a bit different because it's much more conceptual. Here's what the question that I prepared reads. What happens to the major loss when the diameter of the pipe is doubled for a constant length and constant flow rate laminar flow? So basically, what I'm saying is I have a pipe over here and I'm doubling the diameter of it. So this was D, right, in the case 1, and in case 2 I have myself, this is now 2D. And what will happen to the head loss? In order to do that, let's first write the definition of the head loss. Head loss will be F L over D V squared over 2G. As you can see, I'm not asking you to find the value of HL, but rather the ratio of these two cases. So my recommendation in these kind of questions is to assess what happens to the which term. Okay, let's start by the easy one. What happens to the 2G when I double the diameter? Well, nothing, right? It's just 2 times, if I'm using SI, 9.81. So this term is kind of irrelevant to me. So that's not going to make any difference. And if I go up, here's what it says. Constant length. Constant length. So length is constant. So that's out. So that's not relevant to me, right? So now, the rest is changing. And you may be feeling like, what is happening to the V? I thought the V is constant. Well, not really. You'll see in a minute. At this point, let's go ahead and analyze this question. The F is 64 over Reynolds. Why did I write 64 over Reynolds? Because I read the question, and the question is telling me that it's laminar. As we know, for a laminar flow, it's 64 over Reynolds. Okay, so again, this information is not supplied to you in the reference manual. If you look at the Moody's chart, the Moody's chart writes this on it. So that's kind of a loophole to find where it is listed. Okay, but also now let's take a look at what happens to the Reynolds number. That is rho V d over nu. Right? Or if you want to write it, you can also write this as V d over kinematic viscosity. So again, the kinematic viscosity is not going to change just because I doubled the diameter of the pipe. So that's irrelevant. So now you can see, and if I want to plug that in to my equation, you're going to see this 64, which is actually not that important because I'm looking at the ratio. So I have Vd, right? And I have kinematic viscosity up there. So that is L over D V squared over 2G. As we said, this is irrelevant, this is irrelevant. So now you get to see what's going on over here. So this V is like that. I have D squared, and this is irrelevant. 64 is irrelevant. Those are constants. So basically that ratio that I'm asking you to find will be proportional to, not equal to, but proportional to V over D squared. Okay, did you see that? Okay, diameter is doubled. So let's look at the V. How do you think I'm going to get the ratio for the velocity when I double the diameter, but I also keep the flow rate the constant? Okay, do you remember this? The constant flow rate is equal to VA, right? So if I look at like V1A1 in case 1 is equal to V2A2, as I double the diameter, so this will be multiplied by 4x, right? Do you see in the second case? Because the diameter is doubled, so this will be 4x. So then in here you can see that my V2 will be divided by 4, right? In order for this relation to hold true. So now I have myself, so this becomes, I look at the ratio, this is divided by 4. This diameter is doubled, so doubled means 2 to the power of 2, right? That is 4, right? So now you can see this relation becomes 1 over 4 times 1 over 4. As you can see, this is 1 over 16. Okay, so if I go up here, you can see the choice is C for this particular question. Thank you for watching this video.